Hey y'all! So in today's video, we will continue our Python for Data Science series and discuss feature engineering. More specifically, I will give you an intro, review how to understand your data, identifying additional features for analysis, creating new variables, using domain knowledge, handling categorical variables, handling numerical variables, feature scaling and normalization, text data features, time series data features, feature engineering in practice, and review some best practices. As always, this video is timestamped, so if you'd like to skip to a specific section, feel free to by clicking on the timestamp down in the description. So let's get right into it and let's tech talk with Tyler. What is feature engineering? Feature engineering is a crucial step in the data science process where we create new input features from the existing ones. These new features help to improve the performance of our machine learning models. So think of it as making the data more informative and useful for the model to learn better. It's like transforming raw ingredients into a delicious dish that has all the flavors perfectly balanced. In technical terms, feature engineering involves using domain knowledge to extract or create new variables that can enhance the predictive power of our model. These new features can be derived by transforming, combining, or aggregating the existing features in various ways. Feature engineering plays a vital role in the success of any data science project. Here are a few reasons why it's so important. So by creating more relevant features, we can help the model to better understand the underlying patterns in the data, leading to a higher accuracy and improved model performance and better predictions. New features can provide deeper insights into the data and reveal hidden relationships and trends that were not obvious before. Properly engineered features can help in reducing overfitting by ensuring that the model captures the true patterns in the data rather than just memorizing the training set. Well-engineered features can make the data more understandable and interpretable, not only for the model, but also for humans analyzing the results. So in the upcoming slides, we'll dive deeper into various techniques and methods for creating new features, and how to apply domain knowledge to enhance our data for better analysis. Before we start any analysis or feature engineering, it's crucial to understand the data set we're working with. This involves exploring the data set to get an overview of its structure and contents. We typically start by loading the data and taking a quick look at the first few rows to see what it looks like. And we'll use the .head feature function. We also examine the summary statistics to get an idea of the distribution and range of the data, shown via the simple code snippet to explore the dataset. So this code will display the first few rows of the dataset and provide summary statistics like the mean, standard deviation, and percentile for each numerical column. So once we have an overview of the dataset, the next step is to identify the key variables that are important for our analysis. This includes updating the target variable, which is the variable we want to predict or analyze, and the features, which are the variables we will use to make predictions. We can list all the columns in the dataset and look at the distribution of the target variable. By identifying the key variables, we can then focus our analysis on the most relevant parts of the data. Save us some time. So assessing the quality of our data is another crucial step in the data preparation process. We need to check for missing values, data inconsistencies, and errors that could affect our analysis. We also need to evaluate the data types of each column to ensure that they are appropriate for our analysis. So this code snippet will show the number of missing values in each column and data types of each column. So identifying and addressing these issues early on just helps you in creating a clean and reliable data set for analysis. When working on a data analytics or a data science project, one key step is to identify what additional features might be needed for the analysis. This involves looking at the current data set and thinking what new information could help improve the model's performance to answer the business questions or objectives. Sometimes we need to create new features that can fill in the gaps in our current data, providing more context or capturing more complex patterns. So for example, if we are working with a data set containing sales data, we might find it useful to create a new feature that represents the sales growth rate, or combine several features to create a composite score that better represents customer engagement. Domain knowledge is the specific understanding of the field or industry related to the data. It's essential because it helps you and me make informed decisions about which features to create and how to interpret them. And by using domain knowledge, we can then enhance our data set with features that are meaningful and relevant to the problem we are trying to solve. For instance, in a healthcare data set, domain knowledge might suggest creating features based on medical history, symptoms, and treatments that are critical for predicting patient outcomes. The specialized understanding allows us to create more accurate and insightful features. So to give you a practical idea, here are some examples of useful additional features that can be created. Polynomial features, such as creating new features by raising existing features to a power. Interaction features, such as creating features that represent interactions between two or more existing features. Date and time features, such as extracting new features like the day of the week of the month, or the season from date and time data. Aggregated features, such as summarizing information over groups, such as average purchase value per customer. On the screen is a code snippet to illustrate creating a new feature. In this specific example, we're creating a new feature by squaring an existing feature. This can sometimes help in capturing non-linear relationships in the data. By identifying and creating additional features, we can significantly enhance the data set, making it more informative and powerful for our analysis. Let's go over several methods to create new features. By applying mathematical operations like logarithms, square root, or exponents to existing features. We also have interaction features, which is combining two or more features to create a new one, such as multiplying or adding features together. Concatenation. Aggregations, creating summary features such as the mean or sum over a certain group or time period. So on the screen is an example of creating an interaction feature, where in this example, we create a new feature by multiplying two existing features, which can help capture the relationship between them. When working with high dimensional data, some common techniques include PCA, or principal component analysis, which reduces the dimensionality of data while preserving variance. And then we have text vectorization, which converts text data into numerical features using methods like TF, IDF, or word embedding. So in the code snippet for PCA, we reduce the data to two principal components, simplifying the data set while retaining important information. Feature selection helps in reducing overfitting, improving model performance, and making the model more interpretable. Some common methods include correlation analysis via selecting features based on their correlation with the target variable, mutual information via measuring the dependency between features and the target variable, using statistical tests like ANOVA or chi-squared to select significant features. So in this code snippet example of using select k-best with ANOVA f-test, we select the top 5 features based on their ANOVA f-test scores, ensuring that we only use the most relevant features for our model. And by using these methods that we just discussed, we can create, extract, and select features that significantly enhance the performance and interpretability of our machine learning models. Incorporating domain knowledge into feature engineering can significantly enhance your model. By using the domain knowledge, we can create features that are more meaningful and relevant to the problem we are trying to solve. This can involve understanding the business context, industry standards, and specific nuances of the data. For example, in the financial industry, domain knowledge might guide us to create features based on economic indicators, market trends, or risk factors that are particularly important for predicting stock prices or credit risk. Creating domain-specific features means generating variables that are tailored to the unique aspects of a particular field. Here are a few practical examples. Healthcare examples include calculating BMI or body mass index from weight and height. Finance examples include creating a moving average feature to track stock price trends. Retail examples include deriving a customer loyalty score based on purchase history. In this code snippet, to create a domain-specific feature in the medical field example, we create a new feature, BMI, which is commonly used in healthcare, to assess whether a person has a healthy body weight. We now know that applying domain knowledge can lead to significant improvements in the effectiveness of your data science and data analysis projects. So let's look at a couple of real-world examples. A healthcare case study includes a team working on predicting patient readmissions, use domain knowledge to create features based on patient medical history, treatment patterns, and lifestyle factors. So by incorporating these features, they were able to significantly improve the accuracy of their predictive model, which is what we all want. Moving on to a retail project. Analysts use domain knowledge to create features related to customer purchasing behavior, seasonal trends, and promotional effects. These domain-specific features help to enhance the sales forecasting models, leading to better inventory management and increased sales. So by understanding and incorporating domain-specific insights, these teams were able to create powerful features that provided deeper insights and more accurate predictions. Let's go over how to handle categorical variables. One-hot encoding is a technique used to convert categorical variables into binary columns. This is especially useful for nominal data, where categories do not have an inherent order. So each category is transformed into a separate column, and the value of 1 or 0 is assigned to indicate the presence or absence of that category. So this code snippet to perform one-hot encoding will create new binary columns for each unique value in the category underscore column, helping the machine learning model to process categorical data effectively. Label encoding involves assigning each category in the categorical variable a unique integer. This method is particularly useful for ordinal data, where the categories have a meaningful order but not necessarily specific distance between them. So in this label encoding code snippet, each category in category underscore column is replaced with an integer, making it easier for the model to interpret the data. Ordinal encoding is used when the categorical variable has a natural order. So unlike label encoding, the order of the categories is preserved by mapping each category to a specific integer that reflects its order. In this code snippet example, the categories low, medium, and high are mapped to 1, 2, and 3, respectively, maintaining their order. High cardinality refers to categorical variables that have a large number of unique values. So handling such variables can be challenging, but there are several strategies to address this. Using a hash function to map categories to integers, which helps in reducing dimensionality. Also, target encoding via replacing categories with the mean of the target variables for each category. This technique should be used with caution to avoid data leaks. So while these strategies can help manage high cardinality, it's important to evaluate their impact on the model's performance and interpretability. Say that 3 times fast. Binning and discretization involves converting continuous numerical variables into discrete bins. This can help in simplifying the model and handling outliers. So by grouping the data into the bins, we create categorical features that can be easier to interpret and can sometimes improve model performance. So in this code snippet example of applying binning, the continuous numerical underscore feature is divided into 5 bins, creating a new binned underscore feature column. Polynomial features are created by raising existing numerical features to a power. This technique helps in capturing nonlinear relationships in the data. And by generating polynomial terms, we can provide the model with more complex features that can improve its ability to fit the data. This code snippet will create polynomial features up to the 2nd degree for the feature matrix X. Interaction features are generated by combining 2 or more features. This captures the interaction, that's why it's called interaction, between features, which can be particularly useful when the combined effort of 2 features is more predictive than the individual features alone. In this interaction feature code snippet, we multiply feature 1 and feature 2 to create a new interactive underscore feature. Log transformations are used to reduce skewness and handle heavy tail distributions. By applying a logarithmic transformation, we can make the distribution of the data more normal-like, which can improve the performance of many machine learning algorithms. So in this code snippet example, we apply the natural logarithm to numerical underscore feature, adding 1 to avoid taking the log of 0. Standardization is a technique used to scale features so that they have a mean of 0 and a standard deviation of 1. This method is particularly useful for algorithms that assume the data is normally distributed, such as linear regression, logistic regression, and many clustering algorithms. So in this example code snippet, to standardize features, Standard scaler is used to scale the features in the data frame df. Min-max scaling transforms features to a fixed range, usually 0 to 1. This method preserves the relationship between the original data values and is useful for algorithms that do not assume any particular distribution of the data, such as k-nearest neighbors and neural networks. In this code snippet of applying the min-max scaling, min-max scaler is used to scale the features in the data frame to a range of 0 to 1. Robust scaling is used to scale features using statistics that are robust to outliers, such as the median and the interquartile range. This method is useful when the data contains many outliers that could skew the scaling. In this example of applying robust scaling, robust scaler is used to scale the features in the data frame named df. So choosing the right scaling method depends on the characteristics of your data and the requirements of the machine learning algorithms you are trying to use. So it's recommended to use standardization when the data follows a normal distribution or when the algorithm assumes normality, such as linear regression or logistic regression. You'll use min-max scaling when you need to preserve the relationships between the original data values or when the algorithm doesn't assume any specific data distribution, such as the k-nearest neighbors or neural networks. You'll use robust scaling when the data contains many outliers that could affect the scaling process. So by understanding and applying these scaling techniques appropriately, you can improve the performance and convergence of your machine learning models. So when working with text data, it's essential to convert the text into numerical features that machine learning models can process. This process is known as text vectorization. Two common techniques for text vectorization are TF-IDF, known as term frequency inverse document frequency, and count vectorizer. So count vectorizer just converts text into a matrix of token counts. It simply counts the number of occurrences of each word in the text. On the other hand, TF-IDF technique not only counts the occurrences of each word, but also weighs them by the inverse frequency of the word across all documents, giving less importance to common words and more to unique ones. Word embeddings represents words in dense vectors of fixed size, capturing semantic relationships between words. Techniques like word2vec and glov create these embeddings by training on a large corpus of text. So word2vec model creates embeddings by training a neural network to predict context words given a target word. In this example of using word2vec, sentences should be a list of tokenized sentences from your text data. Handling natural language processing, or NLP, data involves several pre-processing steps to clean and prepare the text for analysis. Let's go through them. Tokenization via splitting text into individual words or tokens. Stop word removal via removing common words that don't contribute much to the meaning, such as is, and, the, and and stemming or lemmatization via reducing words to their root form, like running to just run. This code snippet for tokenization tokenizes the example sentence into individual words. And by applying these techniques, you can effectively convert text data into numerical features, making it suitable for machine learning models and analysis. So let's discuss time series data features. Lag features are created by shifting the values of a time series backwards by a certain number of periods. Why is this done? Well, this is done because it helps in capturing the temporal dependencies in the data, which are crucial for time series forecasting and analysis. So for example, to create a lag feature that represents the value from the previous time step, shift 1 will shift the values of the time_series column down by 1 row, creating a new feature that contains the previous time step's value. Rolling statistics are calculated over a moving window, allowing us to understand the trend and variability of the data over time. So common rolling statistics include moving averages and moving standard deviations. So for example, to calculate the rolling mean with a window size of 3, the code computes the mean of the time_series column over a window of 3 time periods, providing a smooth version of the data that can help identify trends. Time-based aggregations involve summarizing the data over specific time intervals, such as days, weeks, or months. This is useful for reducing the granularity of the data and identifying broader trends. So for example, to aggregate data monthly, in this code, we first convert the date column to datetime format because it was object at first and set it as the index. Then we use the resample method to aggregate the data by month, calculating the mean for each month. And by creating these time series features, you can capture the temporal structure of the data, making it more informative for analysis. Let's walk through a real-world case study to illustrate how feature engineering can significantly improve a predictive model's performance. So suppose you and I are working on a project to predict customer churn for a telecom company. The initial data set includes features such as customer demographics, account information, and usage patterns. We start by exploring the dataset to understand the existing features and their distributions. We then identify key variables that are likely to influence customer churn, such as tenure, monthly charges, and contract types. Using domain knowledge, we create new features to capture the customer behavior patterns better. So for instance, we create a feature representing the average monthly spend over the 10-year period. For categorical features like contract type, we use target encoding to encode them based on the target variable, which is churn. We create interactive features to capture the combined effect of multiple features. So for example, the interaction between monthly charges and tenure. After feature engineering, we'll build a predictive model and evaluate its performance using cross-validation. So by applying these feature engineering techniques, we observed a significant improvement in the model's accuracy and predictive power. That's what we wanted. This case study demonstrates the practical impact of feature engineering on enhancing model performance and providing deeper insights into the data. Now let's review some best practices and tips. Data leakage occurs when information from outside the training data set is used to create the model, leading to overly optimistic performance estimates. It's crucial to ensure that data from the test set does not influence the model during training. This is typically achieved by properly splitting the data set into training and test sets before performing any data transformations or feature engineering. So in this example code snippet, to avoid data leakage, train_test_split is used to split the data into training and test sets, ensuring that the test data remains unseen during the training process. Keep track of all the transformations applied to the data is essential for reproducibility and traceability. So document each step, and that'll allow you to understand the impact of each transformation and ensures that the process can be replicated by someone else or future you. So in this code snippet to log transformations, each transformation is logged with a description, creating a record of all the changes made to the data. It's important to evaluate the effectiveness of new features to ensure that they actually do improve the model's performance. And this could be done using cross-validation and feature importance metrics. So cross-validation helps in assessing the model's performance on different subsets of the data, providing a robust estimation of its generalization ability. So in this example of testing and validating features using the cross-validation, a random forest classifier is used to evaluate the model's performance through cross-validation, providing insights into the contribution of the engineered features. So by following these best practices and tips, you can ensure that your feature engineering process is robust, reproducible, and effective, leading to better and more reliable model performance, and you getting that raise in the future since they're gonna love all the work that you do. And that's all that I have. So I hope that by now you have a better understanding of what feature engineering is and best practices and all that than you did before watching this video. So if you have any questions, comments, or any other Python topic suggestions, please leave a comment down below. Also, if you aren't already, subscribe to my channel, it's free, and click the bell icon to get notified when I post another video. Thanks for interacting with Tech Talk with Tyler. I'll see you later.